Welcome. I'm Chetan Nayak, Distinguished Engineer in Quantum Computing at Microsoft, and I'm joined here today by my colleague and friend, Professor Shankar Das Sharma, Distinguished Professor at the University of Maryland, and one of the world's foremost experts on condensed matter physics and quantum computing. We're here in Santa Barbara, California for the annual Station Q meeting, which is a meeting at which scientists and engineers from around the world gather together to discuss the latest results and breakthroughs in topological phases in quantum computing.
So Chetan, thank you very much for asking me to come. I'm delighted to be here for this very special occasion. Of course, I have attended many meetings before, but this is a very special conference. Okay. So can you tell us what is the recent breakthrough in Microsoft research that we'll be discussing in this conference?
Absolutely. So we're very excited to be able to present here at this conference results establishing the underlying physics that will enable topological qubits.
So finally, we have seen some telltale signs of Majorana modes. Is that what you just told me?
Yes. So we've seen, actually, I would say we've seen evidence for the topological phase, for the phase transition into the topological phase, the Majorana zero modes that are present in the topological phase, and have been able to measure the size of the gap, the topological gap, which is a key parameter of measuring the stability of the topological phase, and also, as a result, predictive of qubit performance.
This is, of course, wonderful news, and we are going to discuss this in some depth in the rest of this discussion. Chetan, let me then ask you this question that's kind of a high-level question. So let's say we have a topological quantum computer. What does Microsoft plan on doing with it? Why does Microsoft want a topological quantum computer? What is the goal?
Well, that's a great question. Microsoft's core mission is to empower every individual and organization to achieve more. And nothing embodies that spirit more than quantum computing. To be more specific, we're extremely excited about applications to quantum chemistry, particularly the design of catalysts. So there are certain things that can be well approximated or simulated with classical computers, but there are other problems, other types of chemical reactions that are very difficult, particularly those involving transition metals. So as an example, the Haber process for nitrogen fixation is essential to production of fertilizers. It was discovered over 100 years ago and is still in use. It's very energy intensive. But on the other hand, as you know, it has helped alleviate world hunger. But if we could find better processes for nitrogen fixation, for producing fertilizers that lower the energy costs associated with it and maybe even improve the yields, that could really help humanity. Another example would be carbon capture, which is a problem we're going to have to solve to help alleviate global warming. So there's a number of problems like that. And of course, as you know, there will be many other potential applications that will be discovered on the way that we can't even dream of today.
These are such incredibly cost-intensive things.
Yeah.
You know, this is, I mean, nitrogen fixation solves world hunger, that even if you improve the efficiency slightly with a quantum computer, that would be a huge thing.
Absolutely.
So that's what is going on here,
That's
right?
what's going on here, right.
So that is actually very exciting, because these are real-life applications that help everybody everywhere.
Absolutely. So we're really attempting to solve big problems. And to have a quantum machine that can solve those kinds of problems, we're going to need thousands or tens of thousands of logical qubits, which, if you think about what that means in terms of physical qubits, that, depending on the qubit technology, is probably millions or tens of millions of physical qubits. So in that context, it's really necessary to think about approaches and architectures that have a chance of getting to that finish line. And in that context, there are some factors that are extremely important: fidelity, speed, and size. Focusing on the first one, topological qubits do give us an opportunity, if you can realize them, to have qubits of extremely high fidelity gates, long coherence times. That can be done without sacrificing speed or having qubits that are, or trade-offs in terms of size. So it's the opportunity to check those three boxes to get us to quantum computing machines of scale that has us excited and that has set us on that path. Of course, there's no free lunches. So, you know, it's a difficult path. And part of the difficulty is that there is or has been underlying physics that had to be proven. When the transistor was developed, they didn't have to discover the electron first. right? The electron had already been discovered. So we're in a situation where there really is underlying physics that had to be demonstrated and discovered. And we have made an advance there in proving out some of the underlying physics.
Because not everything that is allowed by physics actually happens in technology.
Yeah.
But if your goal is not just pure research, your goal is eventually a product that will help mankind, I still believe topological qubit is the only way to go. And I think you and I agree on that. Right?
Yes, absolutely, absolutely.
So let me ask you then, can you comment briefly on what the technical ingredients that go into this research and development that's going on at a proprietary level within Microsoft to develop this topological qubit and eventually topological quantum computer?
So the mathematical models of topological qubits and of the underlying topological phases, many of which you yourself have developed, are clear and are well proven. And the concepts are solid, and the equations, the math behind them is really not in dispute at all. What's in dispute is to what extent do those models actually describe real devices?
Exactly.
Devices in the real world, which have significant complications and imperfections. And so
sometimes uncontrolled.
And sometimes very much uncontrolled.
Yes.
So the difficulty involved in making a product or making a technology that works is figuring out, to some extent, what you would call a manufacturing process for a device that realizes that physics, those underlying concepts. And so, the technical ingredients are significant advances on the device design side, backed up by simulation, so that we aren't just doing trial and error to get a working device design. And then significant advances on the materials growth and fabrication side that enabled us to actually realize those designs in the real world, in the physical world, take them from paper to the physical world. And then finally, having the right measurement protocols, infrastructure and measurement protocols to measure the things that actually matter, that are actually giving us insights into both the underlying devices. Are they realizing, is the physical device actually a faithful representation of the design? And also, is the underlying physics that we believe the equations describe actually showing up in the real world? Or is there some other unknown physics that maybe has come in that we didn't,
like
that we
disorder
neglected?
that we don't know of,
like
for
disorder
example.
that we don't know of.
Mm-hmm.
And so those are the technical ingredients, and having those all working together in a feedback cycle is what enabled the recent advance.
So let me ask you a question as a quick follow-up on that. So is this a team effort, or is this a bunch of single PIs doing things like we do in the universities? Our universities are very successful research places, and you have a specific style.
Yes.
But how is Microsoft approaching this problem? Because it sounds like you have various different pieces with various different experts, but there is an overarching theme. So how do you finesse that?
Yeah, no, that's a very good question. That's part of a cultural transformation that our team had to go through in order to get to this point. So this kind of work, what we've done, relied very much on a team concept and a team framework. We are a distributed program, distributed over actually 3 continents and multiple labs. But when I discussed simulation and design, materials growth, fabrication, measurement, I wasn't describing locations.
Right.
I was describing actually functional teams, and those functional teams cut across all these locations. Mm-hmm. And it's the cooperation and coordination between those functional units that got us where we're going. We had to develop all of the technologies that enabled us to design the devices, to build the devices, to measure devices, in order to then see some underlying physics, which in turn seeds the technology that we're trying to build. So it's not this simple scientific discovery first, build a technology later that might work with a, let's say a more academic model. Those things are so tightly intertwined that this is something that occurs very naturally than in a more industrial model.
Now I think that I'm going to ask you to elaborate on the recent Microsoft breakthrough. I know a little bit about it, but I'm looking forward to hearing what you have to say. So please go into some depth of why this is a very exciting thing, why you are meeting here to discuss it.
Yes.
Okay.
So, as I said at the very beginning, topological computing does hold out the promise of a scalable quantum computer capable of solving these extremely valuable problems. In your case, you're interested in factorization, Shor's algorithm. In my case, I'm more interested in quantum chemistry applications. But it relies on being able to create on demand a topological phase within components within a device. Okay, and that turns out to be a subtle to accomplish and subtle to verify, as it turns out. So, and the reason, ultimately the reasons that it's a bit subtle to accomplish is these devices are based on a very novel type of hybrid material, or what's called a heterostructure. It's a sandwich between a semiconductor and a superconductor. And those sandwiches, if the interface is right, can combine all of the control that you have in a semiconductor, control over density, good properties of semiconductor, and the magic of superconductivity in which electrons pair up and have these incredible properties. But if the interface is not of the right type, or if the interface, which could simply be its underlying properties or the imperfections, then you may end up with the worst of both worlds, which is something with very weak superconductivity and very, short scattering times, for instance.
Poor semiconducting properties.
Poor
both.
semiconducting properties, exactly.
This sort of compound hybrid device where
Exactly.
you have a superconductor with a semiconductor, you have to invent this wheel, right?
Exactly. So it's a bit of a specialized semiconductor. And then superconductors have technological uses, but not in combination with semiconductors. So it's that combination that really makes it very unique. And so as a result, all the processes for fabrication are not industry standard processes, not yet anyway. Okay, there will be in the future, I think. But and so a lot of process development had to occur to be able to make these devices. So that's that's a key part of what enabled this. Another aspect, again related to what you just pointed out, is because these are not sort of industry standard device types or fabrication, the simulation capabilities are not the industry standard things that you would be used to simulate.
You cannot just take a
standard CMOS.
COMSOL and apply it. You have to develop it yourselves.
Yeah, exactly. Can't use the standard sort of SPICE modeling that's used for devices. So again, that also had to be developed. So there was considerable development of the tools and technologies to enable the discovery. What the discovery is we have established the underlying physical properties.
Maybe you should tell the actual hybrid structure.
Yes.
You didn't mention what superconductor
Good,
is. That
good.
a secret? You cannot talk about
aluminum.
it?
It's aluminum.
Okay, good.
So it's a hybrid between
Good.
indium arsenide and aluminum.
So the
Aluminum
material
is a superconductor.
has indium arsenide
Yes.
and also has aluminum.
It has aluminum.
Now, is there a magnetic field involved also?
Yes, and there's also a
So
magnetic
it's an
field
incredibly
involved.
complicated structure.
Yes.
Okay, continue.
Good. So it's indium arsenide, it's aluminum. They have to be at very low temperatures. So our measurements
How
are done.
low?
And we do our measurements, and we expect to be operating our qubits in the range of 50 millikelvin. So that is extremely cold. That is much colder.
Is there any technology that uses temperature this low? Maybe in outer space, maybe some.
Well, deep space is, as you know, is about 2.7 Kelvin.
That's even
right?
So
higher. So this is considerably colder.
That
than
is 200
interstellar
times higher.
space.
Yes.
Yeah.
Okay. So this is really a breakthrough if it happens.
These temperatures are achieved in something called, as you know, a dilution refrigerator. These are the lowest temperatures in the universe.
Yes.
Right.
Yes.
It's colder than interstellar space. So it's this combination of indium arsenide and aluminum. It's temperatures of 50 millikelvin, and it's fairly large magnetic fields of around on the order of a Tesla. So and then
4 different things coming together.
Four different things coming together. At least those 4, and then the other 2 are. There are gates. So part of the magic of or the wonderful properties of semiconductors is the ability to control density. Having exquisite control over the density is extremely important here because if the density is too high or too low in the semiconductor, those are also not helpful. So it's to control the density, and finally, limiting the defects and imperfections in the structure. So it's really these 6 things that had to bring under
So
control.
you have not only superconductor, which is a metal aluminum, you also have regular metals lithographically put to control these gates, right?
Exactly. The underlying physics is the physics of a topological phase, because you cannot make a topological qubit without a topological phase, and that really is, for us, it's really at the level of you can't make something like this if you don't have a solid. If this melted and became a liquid, it's a different phase of matter. You couldn't make a table out of it, and these mugs would fall. Topological phase is as different from a conventional, or what's sometimes called sometimes called a trivial superconductor. It's from a conventional superconductor. It's as different as liquid from solid in terms of some underlying properties. Just as this table has rigidity associated with it, a topological phase has a type of rigidity that protects quantum information. And so you can't make a topological qubit without a topological phase. And now topological phases, their signatures are rather subtle because actually their prime signature is in fact that protection of topological information. They have some other signatures, closing and reopening of the gap at the phase transition in which you go into
This
the
is the
topological
superconducting
phase.
gap we are talking about.
The
right?
superconducting gap is an energy gap. That's one of the characteristic properties of superconductors, including topological superconductors. And there's a sharp transition. Just as there's a melting point for a solid, there's a sharp transition from the trivial to the topological phase, as you very well know. And you can detect that transition directly. There are Majorana zero modes, which are states at the ends of the superconductor, and we'll come back to that because we should discuss them. Those are very important. You can find evidence for those through transport measurements, through tunneling conductance measurements that see zero bias peaks. And you can, through a combination of these transport measurements, about a year ago we put out a paper, this topological gap protocol paper, and
that had no data. That was just
that was explaining the measurement protocol, sort of setting the bar that we needed to cross in order to prove out the underlying
So you had
physics.
a bunch of boxes that have to be checked.
Have to be checked,
right?
exactly, exactly. So it's setting out what those boxes are that need to be checked, that we need to see the zero bias peaks associated with Majorana zero modes, that they need to be extremely stable, as they would be for Majorana zero modes, but not for some other accidental resonance.
Correct.
And of course, this all needs to happen in a region in which you've already gone through a phase transition and in which the gap has reopened. And that gap that we can measure, that we have measured, the topological gap or the energy gap in the topological phase, is one of the key properties that tells you how stable it is. You asked me how cold this is. The larger that topological gap, the warmer we can, the higher temperature we can tolerate. The reason
Your
we go to low
temperature has to be,
temperatures-
your temperature has to be not larger than the gap because
Yes.
then it's not going to work. That's
Correct.
what you are saying, right?
Correct.
I mean, yes.
And in reality, it needs the temperature
be
needs
much
to be,
less.
it needs to be several factors,
Correct.
5 or 6 times smaller than the gap. That's a natural scale, and the gap also the inverse of the gap also there's a time scale associated with that, which tells us what our clock cycle can be, how fast we can operate, and a length scale associated with the inverse, which tells us how far separated our Majorana zero modes need to be. So our qubits can be, the larger the gap, the smaller the qubits can be. So when I said at the beginning, hey, you want a quantum machine that can solve a valuable problem in less than a month, because if the solution comes in centuries, it's not helpful, right? No. A quantum machine that can solve in less than a month on a single module. Meaning if you're trying to distribute it over multi-modules and you have to have quantum coherent connections between them, that's an unsolved problem.
Well, that's the problem that's almost insurmountable in regular qubits, right?
So if you want to check these 3 boxes, then what you really want is a topological gap that's large, because it controls the performance of the qubit with respect to all 3 of these axes. And so the excitement is that we have seen that phase, seen the signatures of that phase transition of the Majorana zero modes, and actually have measured the topological gap.
Okay, so let me ask you, let me be a little bit of a devil's advocate, or my usual self.
Yeah.
What makes you believe, if not confident, that you have seen the topological gap? Because this is the big enchilada. This is what we all want, right?
Yes.
So, without going into great details, why are you yourself, now you did not do the experiment, right? So you looked at the data and you are persuaded it has been seen. Can you expand on why?
Yes. So part of it is we actually set a very high bar when we set out this protocol, okay? And the goal of the protocol was to avoid false positives, to set up a protocol to avoid false positives and to avoid hunting for confirmation bias, in the sense of hunting for a desired feature and then stopping when you
that
saw
theory
that feature.
That theory told you should be there.
Should be there.
Because theory has already worked out this topological regime. And you have to avoid finding what the theory told you. And that's a very difficult thing to do, right?
Exactly. So the protocol was designed to take a device, to just scan over its operating regime in the various parameters, the voltage, gate voltages, the magnetic field, and to ask a series of binary questions that could then lead to a yes or no. Does the device have a topological phase or not? And then once the binary is, if it's answered yes, can actually also give you a quantitative metric, which is how large is the topological phase. So, and what the important thing is some important things are, we set the protocol and the bars up before we had any of the data. So we couldn't look at the data and then go back and change the bar based on what we'd seen.
That's the key to avoiding confirmation
Key.
bias.
That's correct.
You set your bars first.
Right.
Okay.
The second thing is we tested out that protocol or validated that protocol on simulated data. So we actually took many simulations. More recently, we've done simulations that incorporate all the features that we know in our devices, the geometry, the dimensions, the levels of the inferred levels of imperfections. But we've also looked at various kinds of models of different device structures. And over many models, the protocol takes the data, just transport data, and is a black box. You feed the data in and it gives you a binary answer and
yes or no.
And a yes or no. And then if it's a yes, then it gives you the value of a numerical answer, quantitative measure of how big the gap is. So it's just as happy to be fed simulated data as real data. And but of course in the simulated data, you can check whether there's a topological phase in the simulated data. You can calculate a topological variant. So you can check the protocol, you can do reality check.
Yep.
And the protocol, we set the bars, we made the protocol stringent enough that we have never seen a false positive in simulated data. Yeah.
Do these simulations include what I alluded to as unknown? And as you know, I have done a lot of work on this unknown, right?
Yes. So the simulations absolutely include disorder. That's a major part of the work involved in the simulations and the expense, because three-dimensional transport calculations in disordered systems, typically per device it's about a week. It's 60,000 cores for a week. And so,
even with Azure, it's a week.
Even with Azure, this is
something universities cannot do. I can tell you that.
Yeah. So no, we're very fortunate to be able to spin up more cores as needed within Azure's high-performance computing division, and so so we have very extensively simulated. Now we have, of course, taken into account the types of disorder that we know are there from measurements, from various measurements of the devices, microscopy measurements, for instance, transmission electron microscopy, scanning electron microscopy, various types of imaging can tell us what kinds of defects we have. And we have also looked at the kinds of defects that are known to occur in other kinds of similar devices.
Exactly. We know a lot about indium arsenide and aluminum separately, right?
Exactly.
So it's not like they're unknown materials.
Right.
And so you have to take into account that disorder.
Yes.
And then you have to take into account what the interface looks like,
right,
where your various microscopy will tell you. And you are telling me all those things were included in the simulation.
Are incorporated in the device. Now, the other thing we do is, of course, we check our simulations against experiments within regimes where we can interpret the data, within regimes where sort of the experimental data is easier to interpret, and do the comparison in order to figure out, well, as you said, there's always, unknown unknowns are, of course, they're unknown. So are there other types of disorder or some other physics or some kind of some chemistry that occurs that's uncontrolled? Well, we try to check it by looking at devices or test structures in regimes that we understand. And a part of that is, as with any fabrication process, there is some amount of device-to-device variation that is uncontrolled. And so we put on all of our fabrication runs test structures to enable us to assess that and incorporate that into the simulations when we try to understand
So
data.
let me then ask you a question with some trepidation. So I'll summarize what you said, and it's an incredibly important development in the subject, that we believe that topological gap has been seen in indium arsenide aluminum hybrid structure. This was the goal, as you know, for more than 10 years, right?
Yes, absolutely.
In how many devices have you seen it? Is it just one or more than one?
No, it's multiple devices. It's not one device. It's
good. I now feel much better.
Good.
Okay, this was my trepidation. Okay.
It's multiple devices, and in fact, there's a couple of things that the devices have to satisfy, and I won't give you an exhaustive list. But
you have seen it more than one device.
Absolutely,
right?
We've seen it more than one device, and I'll make a stronger statement, which is there's some conditions the device have to satisfy. So the devices have to have the superconductor aluminum needs to induce a gap within the semiconductor. That gap can be too big or too small. If the gap is above some minimum value, number one. Number two, there's charge disorder in the dielectric.
Yep.
That which we can actually assess what that is by doing Hall bar measurements on the same chip. if the dielectric charge disorder is below a certain level, and the devices are narrow. Actually, then the width of the device is important.
Absolutely.
Wide devices have many, many subbands, and as a result, the orbital effects are large and the topological gap tends to be small.
Yep.
So if the devices
And inter-subband scattering
and
also.
inter-subband scattering is a big
Exactly.
effect, right? So in devices that are narrow enough to access the single subband regime, have a good induced gap, and have low charge disorder, our yield is over 25%.
All right, so this is
So it's not a 1 in 100, it's over 25%
No, it cannot be.
yield.
If you
Yeah.
told me it's
Yeah.
1 in 100, I would say something is wrong.
Right.
Okay, because of unknown unknowns.
Yeah.
So it's very important, in my opinion, to avoid a syndrome that university research has, where something is published calling it typical data, but it really has been seen only once.
Yeah.
Okay.
Yeah.
And it sounds like you have taken special
Yes.
precaution to avoid that.
Yeah.
Okay. So let
And
me.
in fact, at the meeting, I'll be showing data of multiple devices, and what's interesting is to actually look at also the data of devices that failed, because it's absolutely right. Showing data from one device isn't good. It's necessary to see it in multiple devices. It's also necessary to see the devices that didn't pass,
Absolutely.
and to understand the differences.
Yep.
And
Yep.
so
why do you
that's
think
important
this one has topological gap but that one doesn't? It's very important for us to see what the difference is.
Yeah.
Let me ask you two related questions, and the order doesn't matter. First one is there a plan to someday, because I worry about the proprietary part, someday publish it through peer review, or is that out of question now because of the proprietary consideration?
No, we will figure out a way to publish the results through peer-reviewed journals without giving away the valuable IP of exactly
which
how
I'm
the
sure
devices
can
are
be
made.
done,
Which
but
can
there
be
is a
done,
plan. It's not like it has been it's
Correct.
forbidden. Okay.
Correct.
So other question, again on what you just told us, is what do you see as the biggest challenges in the technical part of these experiments? Let's talk about the experiment rather than the simulation. Now, simulation, I know what it is. You need a larger and larger and more cores, and you need very smart people doing it, right? And but tell me also, you and I are not experimentalists, but tell me also what the big challenges are in developing the device itself, because in the end, the product will be a device.
Yes, it's a fantastic question. So a couple of things. One is there's a measure of semiconductor quality, which is the mobility. Okay, and roughly speaking, that's roughly a measure of how far an electron will travel in the semiconductor before it scatters off of usually off of a defect of some kind. And what we know is the devices have to be relatively clean in the sense of having high mobility, and the mobility is the numbers are on the order of 100,000.
How do you control that experimentally? So how do you get to materials which have high mobility?
So those are trade secrets.
Okay.
So there are ways of improving that.
So this is an issue that's important,
Yes.
and you worked on it to correct it.
Correct. Part of the insight from our simulations, and actually also insights in your own published work, are that this is an extremely important parameter, and we need to develop ways to get high mobility. And so, as I said, a major part of our team is associated with epitaxial growth, which is a growth technique for semiconductors, semiconductor materials, and a large part of it was developing very high quality, high purity high mobility semiconductors.
So in popular jargon, you had to spend a lot of time, a lot of proprietary work in basically making the system very clean.
Exactly.
Okay.
Absolutely.
Right. And the topological gap that you have actually measured in devices and validated by simulations, are they sensible? Let me tell you my definition of sensible.
Okay.
Are they consistent with the kind of predictions I was making? Because these are in Emerson, you know the numbers. So for example, 30 to 50 microvolt is what I was hoping it would be.
30 microvolts.
30 microvolts.
30
Oh,
microvolts.
I'm very happy.
Yeah.
I mean, many of my papers, these are the numbers I have, right?
So yes, absolutely. So let me be a little more specific. The gap, of course, varies over the over the topological phase. But
there's always a gap. It doesn't become zero anymore.
Within the topological phase, there's a gap, and if you look at, say, the top 20, the top quartile, the top the top 25% of it, we've seen 30 microvolts.
Yeah, that is very encouraging.
Yeah.
That is very encouraging, because that's like 300 millikelvin.
Exactly. Yeah.
That is very, very encouraging.
Yeah.
If you go back to the original paper, that's it was -10.
Yeah, right.
Remember that our qubit paper?
Absolutely, yeah.
So that is very, very encouraging. This qubit is going to be really topological.
Yeah.
Okay.
Yeah.
So let's now go to the hardest part, and there,
Yeah.
you will have to speculate a little bit.
Right.
I am persuaded that you have seen topological gap and Majorana zero modes are associated with that. They come together, as you know, a bulk gap and the end modes, right? That's the definition of topology. Let's accept that has happened. Okay. It's a huge physics discovery, huge, gigantic. You and I have been thinking about it for 20 years, right? I mean, so in other systems, in quantum Hall systems and so on.
Yeah.
But the next step is a qubit.
Yes.
The step after that is a quantum computer.
So I would add one more step in what you said. So the step I would add is, so the next step is a qubit, absolutely.
Correct.
The step after that, I would say, is a logical qubit. And by what I mean, by that I mean the following, which is that even topological qubits will have errors. Topological qubits give us a chance to make qubits whose underlying physical error rate is low, and how low depends on the size of the topological gap.
Fidelity is what we wrote down a long time ago, exponential minus delta over t, right?
Right. But these high-value applications we're talking about require many, many steps. So, even if you have a error rate that's, let's say, 10 to the minus 6, if you have an application that's 10 to the 15th steps, then you need error correction, right?
Correct.
And we are talking about those types of applications. So you will still need error correction. So a logical qubit, so having a logical qubit in which you have error correction is extremely important. Now, there's been an important development in that, which we'll also hear about at the conference. Matt Hastings and Jungwon Ha from the Microsoft Quantum Program have discovered a new set of error correcting codes, so-called Floquet codes, of which the Hastings-Ha code is the principal example. And these codes actually fit sort of perfectly with Majorana zero mode based topological qubits, in the sense that the basic error checks that you do, the basic syndrome checks that are done, are exactly the kinds of 2-qubit measurements that are very natural with Majorana zero modes. The other thing is, if you think about, so that's one important piece of the story. The other is, and I think when you talk about engineering challenges, I would say, in my mind, a big one is there's an input-output problem. There's a bottleneck, because a thing that people don't necessarily appreciate is, if you have, there's Rent's rule, right? Which says that, roughly speaking, the number of input-output wires on a CPU is, roughly like the square root of the number of transistors on it. So you can have, a CPU with billions of transistors on it and thousands of control lines, input-output lines. That makes input-output, and even just the spacing and feature size,
the architecture,
right, is vastly different. A quantum computer, every single qubit must have multiple control lines. So if you have millions of qubits, even though that's much less than billions of transistors, it's millions of control lines.
Correct.
And if this whole thing is down in the bottom of a dilution refrigerator, how are you going to get millions of control lines in and out to address every qubit?
Let me just stop you. But this problem, other qubits have even more.
Every qubit. There's a problem for every qubit.
So this quantum control thing, which very early on we did, this is for all qubits. In fact, for other qubits, it's more, because they would need more qubits.
Potentially,
okay?
Yes, correct.
Okay, continue.
So it's a very serious problem. One of the things we'll be hearing about at this meeting is the latest chapter in work that the Microsoft Quantum Program has been doing, led largely by David Riley and his team, and they have developed Krauss-CMOS control chips. So these are CMOS chips with classical computing power that can operate down in the dilution refrigerator, so that rather than trying to run millions of control lines from room temperature, which of course brings heat and noise with it from room temperature, in addition to just how do you get that much.
You will do everything down there.
Do as much control as possible down in the fridge, very closely coupled electrically, but thermally isolated, so that those chips are designed to generate very little power. Well, first of all, to operate at those low temperatures, whereas carriers will freeze out, and so the properties are very different, but also to generate very little heat so they don't heat up the qubits. So there are, as you said, as you think about scaling out from having seen the topological gap to a qubit, to a logical qubit, to a quantum computer, there are a number of very big challenges, which you've called engineering challenges, but actually they're very, very fundamental challenges. Because some of this is fundamental thermodynamics, actually.
Absolutely.
So we have some pieces here that make us very optimistic about our path towards those challenges.
So then let me then just sort it out in my mind. So let's say the Majorana and the topological gap has been seen. Then you do a qubit experiment using the protocols that you already have. That's still kind of a physics experiment. Okay, but that's the ingredient. That's kind of the transistor of the topological quantum computer. So it's very important. That's like, that's like the germanium transistor. Okay. Then you go towards making a logical qubit. And then you start putting them together with this quantum control and everything. So what we are talking about is not just fabrication, growth, measurer, simulator. We are now talking about computer scientists.
We're talking
quantum
about
control people.
Systems engineering.
Systems engineering.
Now we're building a system. And the part that you didn't mention, of course, is all the software. So you've mentioned the hardware layers of the stack. There's also
a huge
several numbers of software layers to that stack, ultimately leading out to applications.
So you just explained why it cannot be done in university. So you have a plan within Microsoft to handle all these things.
Yes. We do believe, I think one of the unique things and one of the things that's very gratifying about working at a company like Microsoft is it's a company that can take on these kinds of big challenges. And there's very few entities in the world, very few companies or even national governments that can take on these kinds of big challenges that require many different kinds of problem solving, solving many different technical challenges.
All at the frontier of knowledge.
All at the frontier and having it work together as a team.
You have to do it in a very seamless, integrated way by everybody contributing.
Exactly. And it is very necessary to have these checks and balances. And I would say for us, some of those aha moments along the way have come when some of the very skeptical people who've been saying, no, this isn't right, said, oh, actually, I ran the simulation, I ran the analysis, and the analysis said, yep, this is real. So part of it is, number one, we established what the bar was early on before we saw the data, and we couldn't move the goalposts. Secondly, there's enough checks and balances, redundancy that no one person or select group of people are both taking the data and analyzing it, or that there's sort of set up the right incentive structure, right? And then the third thing is,
which by the way cannot be done in universities, because universities there is a professor like me who basically decides.
Yes,
and then you'll have confirmation bias, you'll have other problems.
That's right.
Okay.
That's right. And that's been part of our cultural transformation is to move away from that kind of model
effort.
And have that team effort.
But that's not enough, Chetan. Tell me something more. Are you doing something more?
So but in addition, yes, we have engaged a number of external validators who are
non-Microsoft employees, non-ex-Microsoft employees,
non-Microsoft employees, non-ex-Microsoft employees. We have engaged a number of experts, and we have been walking through the data. We're in that process now. We have received reports from a number of them, and we're continuing along that process. And that's very important. We've actually gained insights because we've been very impressed the level to which those people have devoted their time and tried to understand and dig into the data and ask lots of questions.
Professors are good if you give them a well-defined task. They're very good in doing that very scrupulously.
Yes, absolutely.
A few comments I wanted to make that I have been working on this Majorana zero mode and topological quantum computation since 2000. And so I was always convinced it exists because it's something we call free fermion model, meaning it's like band structure. It's like we know copper is a metal. This is something we know. Physics clearly says copper should be a metal, and silicon should be a semiconductor, and carbon should be an insulator, okay? This Majorana thing is like that. There's an equation solution of that gives it. So I was always convinced it exists, it will be seen, and then it will lead to some kind of technology. In science, nothing is guaranteed, okay?
Absolutely.
But I'm extremely optimistic and very, very excited that we have reached the end of the beginning, okay? End of the beginning with this Majorana.
That's a great way to put it.
Okay, and now we are going to start the beginning of the end with the topological qubit, and let's hope that's true.
Great, thank you very much. Appreciate the time.
Good talking to you.
Good talking to you.